Hello everybody. In this week's video, I want to talk a little bit more about the periodic table. And the periodic table all starts with this guy right here, Dmitry Mendeleev. He was a Russian chemist, and in the 1860s, he started jotting down what was the very first periodic table. And what he was interested in is the scientists already had some idea about the atomic masses and the atomic numbers that we have talked about so far. And he started looking at different elements, and he wanted to see how their masses and atomic numbers lined up with their chemical properties. And at first, he had kind of an intuition that as the atomic numbers went up, or as the atomic masses would go up, there would be certain properties that would become more and more prevalent as he went up. But to his surprise, that wasn't exactly true. What happened is instead, as the atomic mass rose, they would have different properties, and then all of a sudden, at some point, it would just kind of double back on itself. And all of a sudden, there would be a heavier element that had properties similar to one of the lighter ones. And then the next one would be similar to the one that was just above this guy, and so on and so forth. And he realized that these different chemical properties were just cycling back around and going over and over and over again onto themselves. And that's where the name periodic table comes from. Periodicity is something that cycles back around, just like a clock, right? You go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 o'clock, 12 o'clock, and then we start back over with 1 o'clock. That is periodicity. So if we fast forward a little bit to our modern periodic table, this is what it looks like now. And we're very, very close to actually filling this bad boy out, actually. We've only added elements down in this region right here in the last few decades. And the ones that we're adding are like really unstable radioactive things. Sometimes they only exist in laboratories. And so chances are we've probably mapped out all of the elements that are at least relatively stable at this point. And we arrange them in two ways. We have groups, these are the rows in the periodic table. And then we have periods, and these are the the periods are the horizontal rows, the groups are the columns. And all of the elements that are in a specific group or column, they are going to have similar properties to one another as we go along with the periodic table. Now, I want to show you a slightly different one than the one that you're going to see in the homework like that. And in this one, we can see that it is numbered. And so each one of these numbers corresponds to a specific group. So we have the group 1, group 2, group 3, group 4, group 5, so on and so forth as we go along, all the way up to 18. And because the ones in a specific group have similar properties, we'll often talk about something like, well, this is some properties of the group 8 elements, or these are the properties of the group 18 elements, and we'll go along and speak about those. There are a couple other things that I want you guys to keep in mind as far as the vocabulary. So, you notice the coloration here in this step-sized kind of line that we draw down here. These are indicators of the metalloids. Okay, and metalloids have properties of both non-metals and metals. And they're actually pretty important to us. Silicon in particular, its properties as a metalloid being a semiconductor are very important to computers. All of the ones to the right of that, including this yellow piece here and the blue column here, these are what they call non-metals. Okay, and this blue column indicates the noble gases, and they're completely mostly inert. They don't really participate in chemical reactions, and we'll talk about that a little bit more in the course, but that's important to know. That's why they're highlighted here. These guys here are pretty much the center of what all like life is made out of. These are our big ones here, and especially across the top here. Most of the molecules that make up you are made out of carbon, nitrogen, oxygen, not so much fluorine. The ones to the left of the metalloids, all of these are the metals, and you can see that that's actually the majority of all of the elements. Okay, these ones, so because there's so many metals, we often break these up into smaller groups so we can talk about them. All the ones from here over to Scandinavium over here and down, these are what are known as the transition metals, and they have properties very similar to what you would think of when I say the word metal. And there's many like very familiar ones in here, like copper or zinc or nickel, gold and silver. We're familiar with these as metals. Over here in this group, these are what are known as the alkaline earth metals, and they tend to exist in nature as like hydroxides. So they're usually basic, and you'll often find them in soil and stuff. That's the alkaline earth part of it. And then over here, we have the alkaline metals. And these guys are going to also be very, very reactive and very important to a lot of things. So you have sodium, that sodium chloride is the main ingredient in table salt. Lithium are very important in batteries. We have our potassium, that's also an important micronutrient. But in general, they have some interesting reactive properties. And then out here by itself, that's kind of special, just kind of different than everything else, is the smallest atom, hydrogen, which has its own kind of unique properties because it is the smallest of all the atoms. Then down here, we have what are known as the intertransition metals, and this is where all of our like larger radioactive atoms are at. Thorium is radioactive. Uranium, you'll recognize that from things like atomic bombs and stuff. Americium is an ingredient that's inside of smoke detectors and is also slightly radioactive. And so that's what these guys are. And a lot of times it's kind of confusing as to why these are out here and just kind of like a little island all by themselves. And really the only reason for that is to condense the table down. And I want to show you what I mean by that. So if we look at this example, this is what the table would actually look like. And it's just simply that it's so long that we often cut this portion out and then write it down here and condense this down. But in fact, the periodic table should look like this, where we just start with lactonite over here and then we end over here at hafnium, and it would be in that group. Now, we talked about how the groups were important, and I want to show you this to show you that some of the groups have special names even. So here, like we talked about, we've got our alkaline metals, our alkaline earth metals. We talked about the noble gases here. This group is also important, 17. That is our halogens. And then 16, we've got our chalcogens. And then 15 are called the pnictogens. And there will be some homework questions on that, so you should be able to recognize that. And then we have what they call the lanthanide series and the actinide series. Here is that piece that I showed you that comes down there. Now we've covered most of the important stuff about the trends and stuff that are going to be important for the homework so far, but I do want to give you guys a little refresher on what we've talked about already. We have a number up here that is going to be our atomic number. We have a number here. This is the atomic mass. We have symbols that are representative of the elements. So the B for boron, for instance, here. Some of them aren't very intuitive, like Fe is for iron, Au is for gold. These are all based on really old Latin names, which is why sometimes they're not super recognizable. Now, the only thing that seems weird and possibly a contradiction to you guys is that last week we talked about the atomic mass as being the number of protons plus the number of neutrons. And on this periodic table, they're all fractions. So are they fractions of protons and neutrons? No. Let's talk a little bit about what is going on, though. Let's talk about atomic masses. So last time we talked, I did not tell you what the unit is for the atomic masses. But these masses are given in atomic mass units. That's what they call them. And that's going to be important. We're going to see that this unit is actually equivalent to another, even more useful unit that we're going to have later when we start talking about stoichiometry. We did also say that the atomic mass number is going to be to the left of the chemical symbol, and it's going to be superscripted. Yet here, when we look at the periodic table that we're given in the homework, up in the top left we see the atomic number. That's because these are separate from one another. This is an entry on a periodic table. I've seen them stylized in a million different ways. Ours just happens to have the atomic number right there. This is a formal way of writing chemical elemental symbols when we're doing like inline text. Like if we were typing something out or writing it out, we're going to write it like this. So this was just an artist's choice. This is the proper way to write it when you are writing things out. Or writing a paper or something like that. We have the atomic mass down here, and then it's written out in words what exactly this symbol corresponds to. There's going to be some homework questions where they ask you to go back and forth between these. They shouldn't be too difficult. So, on to why we have the fractional atomic masses. The reason for that is, as we saw last time, we can have different numbers of neutrons. So 98.9% of all the carbon in the world is carbon-12. It has 6 protons and it has 6 neutrons for a total atomic mass of 12. But 1.1% of all the carbon has an extra neutron. It's what we term carbon-13 with an atomic mass of 13. So, if I put on my periodic table just 12 here, well, I'm going to be, a little off on pretty much every calculation I ever make with this. Matter of fact, I'm going to be 1.1% off. And that is in the best case scenario, where we have a case where the majority of all of the element is one form. There are some elements that are split up almost 50-50, other elements that actually have dozens and dozens of viable isotopes, all of which are going to give some level of contribution. So I need some way to get a good enough number that I can put on here that's going to work pretty well for all my calculations. And the way that we're going to do that is with something called the weighted average. All right. And in this case, what the weighted average winds up being is I'm going to convert this percentage to a decimal form. And I'm going to convert this one to a different decimal form. I'm then going to multiply these two times the atomic mass value for each, and I'm going to add those together, and I get the 12.011 AMU. So it will wind up decreasing my error to use this weighted average over just, for instance, using 12. And that's where these fractional values of atomic mass are coming from that we see on the periodic table. They're allowing us to treat the material as if it is a homogeneous element with an atomic mass of 12.011, which is an approximation, but often will give us a good enough value, pretty much all the time. There are some techniques, like things called like mass spectrometry and stuff, in which case you have to start getting really, really picky with it. But in most calculations, this is going to work out just fine. And I think that's pretty much it for this week. I think you have pretty much everything you're going to need to be successful with the homework.